We are going to talk about terminology now. So now we've moved a little bit away from the strictly math side of things, and now we're going to be figuring out how we can incorporate all these different things together. So some of these will be a little bit of a repeat from the first week, but again, we're just going over a lot of these common terms and knowing how to use them and all that stuff. All right, so our first term that we're going to talk about is a coulomb. So a coulomb is a measurement for the unit of charge. Now, charge, again, is going to be how many electrons are sitting in a specific area. So it is the physical charge of the electrons present. In a specific area. And what that comes out to be, it's the number of electrons present divided by 3.25 times 10 to the 18th electrons. Okay? And coulombs is going to be designated as a C. So coulomb designated as a C, and it is a unit of charge coming from charge, which is Q. So the thing we're measuring is charge. The unit of charge comes back to coulomb, which is the capital C, which is what we talked about in our SI units section. All right, so again, coulomb is unit of charge based on the number of electrons that are present in an area. All right, our next terminology word is conductor. And in the electronics world, a conductor is a material that allows charge or current to flow through it. Okay, so pretty simple. Conductor allows current to flow through it. Constant voltage source. A constant voltage source is what we are going to be using primarily in our day-to-day activities as far as lab goes. So what this does is it provides a constant voltage with varying current. So it will do whatever it needs to do to the current to maintain the voltage. This is where we get things like a 5-volt source, a 9-volt battery, a 1.5 volt A or AA battery, AA or AAA battery. Okay, so it's going to put out whatever current it needs to what it's connected to give you this voltage at all times. Now, in comparison with that, we also have what is called a constant current source. C-U-R-R-E-N-T. A constant current source does just the opposite of this. This provides a constant current with varying voltage. So if you needed a tool that spit out a specific amount of current to turn a motor or to turn, or an arc welder or something like that needed the current more than the voltage, then you would use a constant current source. So that's going to spit out, like I said, just your values as far as current goes, but keeping the voltage variable and changing whatever it needs to be. You may not even care what the output voltage is, you just care what the current is. So this is going to give you an option of 2 amps or 5 amps or 20 amps, depending on what your application is. That's what your constant current source is. Okay, the next one we're going to talk about is a circuit breaker. So a circuit breaker is a mechanical device so a mechanical device with a specific current rating that physically trips and opens the circuit when the current is greater than the rated current. Meaning, when we flow too much current through a device, it's going to trip. So in our houses, a lot of times, this is where you'll see it, you have breakers that are labeled as 10 amps, 20 amps, 15 amps, 100 amps, things like that. So what that means is that's what that breaker is rated for. If the current ever was to exceed that posted limit, such as 15 amps, it's going to physically break, which means it creates a spot that current cannot flow through, and thereby saving you or your product or your property or whatever it is from having excess current running through it. We use these a lot in lab. We have them in the walls. We're going to be using circuit breakers, but we're also going to be using fuses. So kind of the same idea with this and a fuse and a circuit breaker. A circuit breaker is a mechanical device. This also can be reset most of the time and reset back into where there's no current. You flip the switch, turn it back on, and now it'll allow current to flow again until it exceeds the maximum rating. A fuse does the same thing. This is a mechanical device which burns up when our current is bigger than its rated value. This one is a one-time use. So again, a mechanical device, it has a little filament that runs from end to end, and if it gets too much current in there, it physically burns up, creating an open, and it doesn't allow current to flow through itself anymore. Again, it's one-time use. The difference being why we use fuses and circuit breakers. A fuse is there to act as a quicker option than the circuit breaker was most of the time to shut down power. And it's designed that maybe we do get spikes once in a while, and those things we kind of take into account, but we want to be able just to, keep it from getting into our other parts of our system and blowing things up, but it's something we can go back and replace, hopefully not all the time. If you're constantly breaking your fuse or constantly breaking your breaker, you probably have something else going wrong with the circuit, and that needs to be addressed first. All right, so then after the fuse, we are going to be looking at a potentiometer. A potentiometer is a variable resistor that provides multiple resistances that can be varied up to its rated value, meaning the potentiometer. So what this is going to do is if we have a 10K potentiometer, the schematic symbol is going to look like this, and we have these contact points. So we've got contact A, contact B, contact C. Now the idea with this potentiometer is it has a knob on it, and the knob is going to look something like this, at least for the ones that we're going to use right off of the bat. and it's going to have a base that comes around, and then there's going to be 3 prongs that come off the edge like this, and then the device looks something like that. So there is your A, your B, and your C. So this knob is going to rotate back and forth until it gets to a hard stop, and what that does is going to shift this point either up or down, and it changes the ratio of the resistance between point A and B and between point B and C. A to C stays the same regardless of where this potentiometer arm is at. All it is doing is changing what A and B is compared to B and C. A and C will stay the same. So this is going to be the ratio of resistance. And we can get multiple resistors. Most of the time we're going to end up with 2. If your variable resistor can have more connection points, so you'd have more variation onto that and more actual resistors, things like that. It just depends on what you're looking at. The difference being is we have the potentiometer. We can use it in another method, and we can use it as a rheostat. So a rheostat physically is the same device as a potentiometer. But a potentiometer by itself is going to change the ratio of A to B compared to B to C. But what happens is we are going to take our schematic and we're going to come out with this. So there's point A, here's point B, here's point C. We're going to connect point B and C together. So essentially what happens if we just put a piece of wire there, the ratio of A to B is going to change. B and C is essentially going to equal 0. So this is going to be A to B compared to 0. But then my entire resistance, A to C, is going to change to give us that A to B ratio. So we're using the same device, but using it 2 different ways. The rheostat turns it into a single output or single option with 1 resistance. That is variable. So a potentiometer, when we change it, it changes the ratio of A to B and B to C, but it maintains the entire resistance of A to C. With the rheostat, we do the same thing as we're changing that ratio, but most of the time that ratio from B to C is ignored and taken out of, so we don't even have it in the circuit, and so we're left with 1 value, the A to B value, which can change depending on how we adjust the knob, and that's all we get. So same device, 2 different options on how to use them. Okay. Next thing we're going to talk about is circuit configurations. So we've got a series circuit. A series circuit has 1 current path. There's only 1 option for it to go. It goes from this component to this component to this component to this component and back to the start. 1 current path, and it has a complete path. A parallel circuit has multiple current paths. But it also has complete paths. And mostly by design. So we can create parallel circuits that aren't complete paths until they're connected, and we'll talk about those in the next week's section when we start talking about parallel circuits. But there's 2 options we can have. And then we can even mix and match these, and we can have series parallel, which are combinations of this section is in series with one current path, and then another section that can be in parallel with multiple current paths, and mix and match and go back and forth between them. So we'll be talking about these a lot. Specifically this week as we'll get into series. Next week we'll get into parallel. All right, the next term that we're going to use, and it's one of our fundamental laws, is Kirchhoff's voltage law. We call this one our KVL. So Kirchhoff's voltage law says all drops, so all voltage drops, and supplies, basically inputs, must equal a net of 0. Meaning my input must equal my output. Okay, I have to account for everything. This starts getting into the laws of conservation of energy, meaning energy is not created nor destroyed, matter is not created nor destroyed. It has to be accounted somewhere. We can use it, we can input it, but it all has to balance out to equal 0 in the end. All right, next thing we're going to talk about is series aiding and series opposing. Series aiding means we have voltages or currents that add or work with each other. Our series opposing is our voltages or currents that subtract or fight against each other. And we'll talk about those a little bit more later as well when we get into some of the actual theory. Okay? So series aiding is they add and they work with each other. Series opposing is they subtract and they fight against each other. Next one we're going to talk about is a closed circuit. This is so we got a closed circuit and an open circuit. Okay, these are circuit conditions. These are designed. So designed circuit conditions. A closed circuit has a current path from and to our power supply. An open circuit does not have a current path. And then from power supply to and from. Okay. Versus a short and a open. These two are failures. A short is a sudden decrease in resistance approaching 0 or trying to. An open is a sudden increase in resistance approaching an infinite value. So an open circuit versus an open is the open circuit is designed to not have a current path, basically giving it an air gap, which is a huge resistance compared to everything else, so no current's going to flow that way, versus an open by itself, the one word, where that is just a sudden increase in the resistance. So something that was allowing current to flow has now burnt up and is no longer there to regulate the current. A short is a sudden decrease in resistance, like a piece of wire falling across something that is supposed to be connecting or dropping voltage. So we've got design conditions, a closed circuit or an open circuit, and we have failures, a short and an open. Okay, next term is electrical shock. Electrical shock. Electrical shock is the physical sensation of current running through the body. Through the body. Not good. If you can feel it, you're getting some electrical shock. Sometimes you can't feel it. It might be so small, doesn't mean it's not happening. But the biggest thing about the electrical shock is that's the physical sensation and the physical movement of the current running through your body. Okay, and then the last three. We are going to talk about precision, accuracy, and error. Precision is repeatability. The more precise you are, the more often you get the same answer when you do things. So that's repeatability. It happens more and more correctly, and it happens the same way every time. Accuracy is the correct answer. The correct answer. And error, it's the difference between an accepted value and a measured value. Error is going to be determined mostly in lab, and we're going to be determining that by what we calculate should happen by versus what actually happens. So a lot of times the error, we're going to put it into a percent. We are going to be looking for, in this class, a 5% error, so you can be 5% bigger or 5% smaller of the value and of what is calculated versus what it should be, and we are going to be considering that a good value for that. Another way to think about this is to think of a bullseye. So if I'm shooting at a target, guns, arrows, marbles, whatever, I'm just trying to, throw something or put something on a target. Precision is when you're able to take all of whatever you're doing and group them in a tight group together somewhere on the target. This is precision. I'm doing the same thing over and over and over again and getting the same results. Accuracy is how close am I to the target of my problem? What is my target? How close to the center am I? So my target is my accuracy. I can be precise and not be accurate. And I can take that grouping and then I can work on my accuracy by changing something and doing it repeatedly. I can actually then take that and walk it in to have high accuracy. Accuracy is something that is very easily learned and very easily changed. Precision takes a lot more work and it's a lot harder to achieve because it takes longer. You have to build up habits. You have to be able to get into the way of doing things. So you can build up your precision, and once you have your precision dialed in, then accuracy is very, very easy to change. It's just small corrections to get it into where it needs to be, as long as we're getting the same value over and over. And then again, error, it's the difference that we are between these, and there's different ways to find that and stuff like that. But that's the idea behind these. We want to be very highly accurate, very highly precise, and have very low error. That is the end game. We want, when we're shooting at this target, we want to be very precise and very accurate in the center column. Again, if we're just kind of taking pot shots at this thing and just hoping we do our best and seeing what sticks across the board, our precision is going to be all over the place. And that's how it starts out in the beginning, is I have very low precision, very low accuracy. And then as I start getting familiar with the material and start figuring out the way to do things, I can dial my precision in through a lot of hard work into being very precise. And in that process, I can be adjusting my accuracy as well. But once I'm very, very precise and have high precision, I'm getting the same thing over and over and over again. If there's some slight corrections I need to do to get my answers correct, or my end points or end goals or whatever it is, I can then walk my precision in by changing a couple of things and then maintaining those changes in my routine for what I'm doing. So very easy to change accuracy. Precision comes with time.